Notes 9.4 are on the topic of the comparison tests. The comparison test is the following. You have two series, Series A, Series B, and they have positive terms. If Series B is convergent and it is greater than A for all n, then A is also convergent. If Series B is divergent and it is smaller than A for all n, then Series A is also divergent. The most common series to do this comparison with are p-series and geometric. So your series will be A, and you have to pick a series on your own to compare it with. So the first ones you want to think about are either p-series or geometric series. So they're listed here to remind you. The p-series converges if p is greater than 1 and diverges if p is less than or equal to 1. Geometric series converges if the absolute value of the common ratio is less than 1, diverges if the absolute value of the common ratio is greater than or equal to 1. For our first example, we will determine whether this series is converging or diverging. For a large n, I'm noticing the dominant term in the denominator is 2n squared. So my focus is on this 2n squared. Therefore, I'm deciding to compare with the series 5 over 2n squared. First, I'll do the comparison. Our series is 5 over 2n squared plus 4n plus 3. And I'm comparing that with 5 over 2n squared. Notice how the denominator of our series is greater than the denominator of the comparison series. Since the denominator is greater, then the fraction is smaller than the comparison series. Now I'm going to look at that comparison series. I can rewrite it as 5 halves times the series of 1 over n squared, and that looks exactly like a p-series. So this is a p-series with p equal to 2. That's greater than 1. Therefore, the comparison series is convergent. And that means our series is convergent. Remember to mention which test you use to prove convergence. Another example, our series is 5 to the n over 4 to the n minus 3. This looks a lot like a series of 5 to the n over 4 to the n. So I'm going to compare with 5 to the n over 4 to the n. Write down our series and compare that with the comparison series. For our series, the denominator is smaller than the denominator of the comparison series. Since our denominator is smaller, that makes our series larger. So the comparison series is smaller than ours. Now look at the comparison series. 5 to the n over 4 to the n can be rewritten as 5/4 to the n power. This is a geometric series. This is a geometric series with r equals 5/4. Since the absolute value of 5/4 is 5/4 and that is greater than or equal to 1, then the comparison series is divergent. And that means our series is divergent by the comparison test. If you find that the comparison test is not working and you believe it should be working, then perhaps you need to go to the limit comparison test. The limit comparison test takes those two series, our series and the comparison series, as long as they have positive terms, and we take a limit of their quotient. So set up a limit of the ratio, our series with the comparison series, and see what value you get when you take the limit. If c is a finite number that is positive, then both series are converging or both series are diverging. For example, if we go to test this series and our first instinct would probably be to use the comparison test. We would choose 1 over 2 to the n to compare with. If I look at 1 over 2 to the n minus 1, that's our series, and compare it with 1 over 2 to the n, notice that our series has a denominator smaller than the comparison series. So that means our series is bigger. Well, when our series is bigger than the comparison series, we want the comparison series to be divergent. But 1 over 2 to the n is a geometric series with r equals a half. Since absolute value of 1/2 is less than 1, then our comparison series is convergent. We didn't want it to be convergent because our series is greater than that one. This means that the comparison test does not apply. However, it seems like our series, 1 over 2 to the n minus 1, should be convergent. So we will use the limit comparison test to check again. Set up the limit as n approaches infinity of the quotient of these two series. Put our series on top, put the comparison series on the bottom. I'm going to change the quotient of these two fractions into the product of them. So that's 1 over 2 to the n minus 1 times 2 to the n over 1, which gives us the limit of 2 to the n over 2 to the n minus 1. I'm going to divide top and bottom by 2 to the n. That will give me 1 over 1 minus 2 to the n. Now when I take the limit, I'll get 1 over 1 minus 0, which equals 1. Since the limit equals 1, which is positive, and our comparison series is convergent, then our series is convergent as well. Let's practice the limit comparison test on number 24. The series I would compare with would be 1 over the square root of n squared, because in the denominator, the n squared term has the greatest effect on what's happening in the denominator as n approaches infinity. Of course, 1 over the square root of n squared is the same as 1 over n. This is the harmonic, and you already know that the harmonic is divergent. Set up the limit, put our series on top, put the comparison series on the bottom, rewrite that as one fraction. You might also put it under the same radical. I will divide top and bottom of the fraction by n squared, and then I'll take the limit. The result is 1. That is a finite number that is positive.